Hello, in this lecture, we are going to start with Fourier transforms, and today we are going to see some of the introductory aspects of the same. That is, we want to see how the Fourier transform has evolved. Uh, I would assume that there is some sort of you have some sort of understanding of Fourier series. Although I'll go through the Fourier series once a while also, while I'll be doing waves and oscillation. Right now, I will be more focusing on your mostly focusing on uh, Fourier transform today, and mostly I'll be assuming that you know much of the Fourier series. Okay, so much of the Fourier series I'll assume that you know, and from there onwards we'll start. Okay, so let us start with without wasting the time. We should start with this thing. Okay, so let us start with the Fourier transforms. Okay, so first thing is uh, you, you might have studied Fourier series in your graduation or sometimes. Okay, so I'm going to just remind you what you've studied till now. And so for example, you've studied that if you have a periodic function, then you can represent this periodic function in terms of linear combination of sinusoidal function, linear combination of sinusoidal function. And this you might have done in your graduation classes a lot many times. You might have been given some square wave input or some triangular input. For all those inputs, you might have written what you call as your Fourier series. So you know that you've done that. So if I say that my function fx, okay, and the function fx, if it is periodic, it can be, and let's say it is periodic with period t. And what does a period of function imply? Period of function implies that if I'm saying that my function is periodic with period t, then f of x plus t should be equals to f of x. And here t is greater than 0. Here t is greater than 0. So this is how it is. And what are the criteria that, for example, you might have seen that even the function like square impulse or triangular sawtooth wave, all these functions have some sort of Fourier series representation. So what is required from function? A function can admit finite number of discontinuities. Okay, so one thing is clearly, that is function can have finite number of discontinuities. Finite number of discontinuities in a period. So for those functions also you can write the Fourier series representation. So if you remember your sawtooth wave, so it is clearly discontinuous. So if you see here, like you can see that the function is discontinuous. Okay, so from if you move from or for example, let's say this is to continuous. Let's say for example the square wave. So what is one thing that is required? Function can bear at most finite, can have finite number of discontinuities in a period. If that is the case, then also we can write the Fourier series representation, provided function fx is periodic. So one thing is clear, that if function is periodic, even if it accommodates some of the finite number of discontinuities in one period, we can represent this periodic function in terms of an infinite Fourier series given by this. I think it is a naught, and then you can write summation n equals to 1 to infinity, and I can write an, and if the period is t, what I'll write cos 2 pi nx upon t. And this is something that you are familiar. I mean, this is something that you know from your graduation. Although probably another class when we'll be studying waves and oscillation, probably we'll take this up. But right now I'll assume the knowledge of Fourier series. Okay, right now I'll assume the knowledge of Fourier series. Okay, so you can write your function in this sort of representation. So your function can be written as a naught plus summation n equals to 1 to infinity an cos n pi x t upon plus bn sine 2 pi nx upon t. Right? And here function fx is periodic, point number 1, and function can have at most uh, finite number of discontinuities in one period. Okay, So such functions can even be written in form of your Fourier series representation. Okay, now you know that these constants are called as Fourier coefficients, like an, a naught, and bn. All these three terms are called as your Fourier coefficients. And you know that how to write, I mean, that is quite easy to see that sine and cosines are orthogonal to each other. So in order to extract a and b, multiply this entire expression by cos 2 pi nx upon t. In order to find b and b, multiply both sides by sine 2 pi nx upon t. And in order to extract a naught, we just integrate it from minus t2 plus minus t by 2 to plus t by 2. So that I'll write here. So what I'll do, what will be a naught? I think this is something that you know again. This is minus t by 2 to plus t by 2, 1 upon t here written, and then you can write f of x dx. Similarly, you can write an. What is an? It is simply 2 upon capital T minus t by 2 to plus t by 2, and then you can write f of x, and then you can write cos of 2 pi nx upon t, and then dx. And what is bn? Bn is simply 2 upon t, then minus t by 2 to plus t by 2, and then again you have this f of x, and then you have this sine of 2 pi nx upon t dx. So these are your Fourier coefficients, which we can extract from each of these following. And from complex analysis, we've done complex analysis. We know that how to represent these cos and sines. So you can represent these cos and sines in form of sines and cosines can be represented in form of your exponentials, that is e to the power iota x. Okay, obviously some 2 pi n x t would follow. So what I can do, I can, if I use these things up, so what I'll get, I will finally get that my fx can be written as a naught. Then I can write summation n equals to 1 to infinity. I'll get an, and here I will write e to the power iota 2 pi n x upon t plus e to the power iota minus 2 pi n x upon t divided by 2 plus bn, and here you can write e to the power iota 2 pi n x upon t minus e to the power minus iota 2 pi n x upon t divided by 2 iota. Okay, so this is how you write things up. Okay, this is how you write things up. Now what needs to be seen, that I'll do certain things. So for example, I'll write this thing uh, although the derivation is not required, but still I'm giving you some sort of idea here. I'll write it from n equals to 1 to infinity, and what I find is that if I multiply plus minus iota, so I'll get an minus iota bn divided by 2 times e to the power 2 pi n x iota upon t, and again I will get plus, I think this would be an plus iota bn upon 2, and I think this will be e to the power minus 2 pi iota nx upon t. Okay, and let us say this is, let's say your dn, let's say this is your cn, so things will be easy, and let's say this is your, let's say c naught. Let us say this is your c naught. Instead of a naught, I'll use the c naught term. So what will happen, you can write this entire thing up as f of x as simply c naught, and then you can write it as summation n equals to 1 to infinity, and then you will have the cn, and then this entire thing will prop up, that is 2 pi n x upon t, and then you have this plus summation n equals to 1 to infinity, and then you have this dn e to the power of minus 2 pi iota nx upon t. Okay, this is how it is. And then you see what I can do is I will define this dn as simply c minus n, because what it is doing, it is taking care of negative, like here you can see minus is there. So if I run the index from negative side, so for example, if I place n equal to 1, so what is happening, it is coming out as minus 1. If I place n equal to 2, this will become minus 2. So basically what is happening, it is equivalent to running the index from negative. Okay, so what I'll do, I'll simply write this dn as c minus n. So I'll show you here what I want to say. So I'll write dn, this is like minus 2 pi iota, and nx upon t, and from n equals to 1 to infinity. So instead I will write summation n equals to 1 to infinity. Instead of dn I will write simply c minus n, and here you have e power minus 2 pi iota nx upon t. And what I'll do, I'll simply take minus n as m. So I'll take minus n as m. So your summation lower side will become m equal to minus 1 to minus infinity, and it will become c m e power 2 pi iota mx upon t. Whether you write m or whether you write n, it is one and the same thing. So you can write here again summation n equals to 1 to infinity, n equals to minus 1 to minus infinity, and you have the cn e power 2 pi iota nx upon t. So this entire term, that is the last term, would become this, varying from minus 1 to minus infinity. So instead of all these things, so if you can write this in this form, so basically what is happening, you are running the sum from minus infinity to minus 1, because sum is after all commutative, where you, even if you want to run from c minus, if you want to add c minus 1 whatever is here plus c minus 2 plus c minus 3 dash 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 c minus infinity, or you run from c minus infinity to all these things like till minus 1, this will be one and the same thing. What I want to convey is that since addition is commutative, so you can even interchange these limits, like you can place n minus infinity here and n equal to minus 1 here. I hope it is clear. So what will happen, 0 is taken care by this. So if I want to find what is n equal to 0, at n equal to 0, this will be c0, and this will be e power 0, this will be c0 only. So basically what I'll do, because of this, what I can do, I can write this entire series which I'm encircling right now. This entire series can be written in the following manner. And what is that? So I'll simply write that my f of x can be written as summation n equals to minus infinity to plus infinity cn e power iota 2 pi nx upon t. So in this, everything has been taken care of. So your terms with the negative coefficients, negative subscripts, everything has been taken care of. So this is sometimes referred to as complex Fourier complex exponential series, or I don't know what term should I use for it. So I should use complex exponential series. Complex exponential Fourier series. And this is supremely important topic I'm saying when it comes to examination. Fourier series has got a lot amount of importance in your exam. Okay, so I hope this is clear. I would urge that if somebody has doubt, kindly write in the comment box so that I can know that if there is some doubt. So I'll wait for people to write some sort of doubts if they have any. So these are called as complex. This is called as your complex exponential Fourier series. Okay, so somebody has got some doubt. I don't know what is the doubt. Just let me know. Somebody says that the integral limit should be from 0 to t, right? What integral limits? Sir, how cn equal to mine? So okay. So देखो, what I've done, I have see देखो, इसको index को समझो. देखो, ये जो चीज दिख रही है ना, this one. So at least there is someone who's asking this doubt that how I've been able to use this tn here. So what I'm doing is, see, you just expand this term up. So you'll get what I'm trying to say. I'll write it as d what you can say d1 and this will be e की power minus 2 pi iota x upon t. Then d2, this will be e की power minus 4 pi iota x upon t. This will be d3 e की power iota minus 6 pi iota x upon t. So basically what I have done is I have tried to write it as a different constant. So let me write not d1 but write c1, because after all these cn's are just constants. They are just constants. So it's just a matter of symbol. So if I write instead of d1, if I write c minus 1, so it will be e की power minus 2 pi iota x upon t. This will be c minus 2 e की power minus 4 pi iota x upon t. And then this will be c, just see, basically it may happen that d3 is 4. This is also 4. Basically just have changed the symbol. Just have changed the symbol so that the series looks quite compact. So here it will be c की power minus 6 pi iota x upon t, so on and so forth. So what I want to say is that if I do in this manner, can I not write it? Can I not write this as c minus n e की power minus 2 pi iota n x upon t, where n varies from 1 to infinity? And then instead of n, if I use this, like for example minus n, so if I use minus n, what will happen? So minus n, if I take as that as minus n, so it will happen, this is like cn, and this will be e की power minus 2, sorry, this will become plus 2 pi iota n x upon t, and this is simply equivalent to writing n varying from minus 1 to n equals to minus infinity, and this is what, this is equal to cn e की power 2 pi iota n x upon t. So if you do that, and the limits why I have taken from not from 0 to t in Fourier series, this is how it is taken, from minus t by 2 to plus t by 2 if the function is periodic, if with period t. So this is how we take minus t by 2 to plus t by 2. This is from the Fourier series. So somebody is asking that why not limits from 0 to t. So I'm giving you the answer that if you have period t, then the limits are from minus t by 2 to plus t by 2. If you had n, then it would be minus n by 2 to plus n by 2. Do I need to say, is there any doubt overall? So basically what will happen, because of this particular thing, you see that all these negative sort of terms, negative in terms of powers, are getting assumed here. Yeah, so exponential has become positive, right? So exponential term has become positive. This is what I've written. So exponential term has become positive here. So this will take care of all the negative power terms, because see this exponential has see what I want to say. You got this particular point, right? Now you see there is another term that is going on. So fx is equal to a naught plus then cn e की power iota 2 pi n x upon t sums n equals to 1 to infinity, and then you have this another term that is sums n equals to minus 1 to n equals to minus infinity cn e की power iota 2 pi n x upon t. Don't get confused with cn. Cn is just a constant. Don't worry about it. Just think about all these things. Now see what is happening. You write this as c naught. Instead of a naught, you just write c naught so that I can compactify it in one form. So if you write here, this will be c1 e की power iota 2 pi n की जगह 1 आएगा x upon t. Then c2 e की power iota 4 pi x upon t plus c3 e की power iota 6 pi x upon t, so on and so forth. Put n equal to minus 1. So you will get c minus 1 e की power minus 2 pi iota x upon t. Then plus c minus 2 e की power minus 4 pi iota x upon t. So what you are seeing that all these terms, 2 pi x upon t is here, minus 2 pi x upon t is here, 4 pi x upon t is here, minus 4 pi x upon t is here. So basically what is happening, if you see, can you not write this entire sum as simply summation cn e की power iota 2 pi n x upon t, n varying from minus infinity to n equals to plus infinity. This is what I'm trying to say. This is what is known as your complex exponential Fourier series. Should I repeat it, Bharat? In the second line, c minus 1 term. Okay, so you're not actually not getting what I want to say. See, 1 मिनट देखो, आपका फंक्शन जो है, if it is a periodic function it can be represented as this. ठीक है, जैसे कि क्या लिखा था हमने, सी एन, इट वॉज सी नॉट एंड इट वॉज रिटन एज exponential iota. Just don't worry, I'll resolve it out. This is it, this is what you've written, right? And then instead of dn I had written my c minus n. Here I had c minus 2 pi iota n x upon t, n varying from 1 to infinity. Here also n varies from 1 to infinity, right? Now you see, this is how you can write when your sines and cosines have been replaced by the uh, complex exponential term. So see here, if you have c naught, if you write n equals to 1 here, you will get c1 exp iota 2 pi x upon t. Then you see, you write n equal to 2, you will get c2 exp iota 2 4 pi x upon t. Then in n equal to 3, if you place, you will get c3 e की power iota 6 pi x upon t, so on and so forth. Now you come to this point. If you place this n equal to 1, or you will get c minus 1, and then you will get e की power of minus of 2 pi iota n equal to 1, you will get c, uh, this is like, instead of dn, I have written c minus n. Okay, so this is what is the change. Okay, now this will give you e की power minus iota 2 pi x upon t, then c minus 2 e की power minus 4 pi iota x upon t, and then c minus 3 e की power minus 6 pi iota x upon t. Now what you can do is, instead of writing this time and again, what you are doing, see here what you are doing, it is equivalent to writing summation n equals to 1 to infinity from c minus n e की power 2 pi iota n x upon t. So basically your counter, that is your limits of sums, are going from positive 1 to positive infinity. Now instead of minus n, if I replaced minus m by m only, then what will happen? So if I replace minus n by m, so what will happen? These limits will become from m equal to minus 1 to m equal to minus infinity cm e की power 2 iota m x upon t. So whether you write m or whether you write n, this is one and the same thing, because after all, like limits are going same, so I can change the variable. So I'll write n equals to minus, in fact write minus infinity to n equal to minus 1, because after all some addition is commutative. Whether you add from minus infinity to minus 1 or you add from minus 1 to minus infinity, they are same thing, because addition is commutative. Whether I go with this order from here or whether I go from this order, this is one and the same thing. So what I can write here, I can write Cn e की power iota 2 pi n x upon t. I hope it is clear now. It is from minus infinity to minus 1. So this particular term, the last term, will take care from minus infinity to minus 1. किसका take care करेगा? Summation Cn e की power iota 2 pi n x upon t. The बीच वाला term, this intermediate term, will take care from 1 to infinity. Which term? Summation Cn e की power iota 2 pi n x upon t. And then this c naught term is there. So basically what you are doing is, you can now write your function f of x is equal to summation. Don't worry about the cn. Cn is just a constant. It is from n equal to minus infinity to n equal to plus infinity e की power iota 2 pi n x upon t. So this is what you call as your complex exponential Fourier series. I hope now you have resolved the doubt, or is there still a doubt in this? I hope it is clear. Is there still a doubt? Yeah, it will that is what I'm saying. It is reflecting in. Okay, you want to say that. Okay, that is. No, no, no. I got your point. I got your point. You what you want to say is that if I'm replacing d, like I'm just giving it a symbol, right? No, right? Just giving it a symbol so that you can see that in synchrony. So don't worry about it. मतलब समझ रहे हो मेरी बात? I do understand your point. The child is asking that if you replace dn by c minus n, why you are not changing minus n to plus n here, right? This is what you're writing. I am just saying that I am just changing it for the sake of understanding. Nothing else. You just think of it as some constant being replaced by c minus n. So just the change of this index, just to make sure that you should relate to all these things. Otherwise, uh, I'm not actually replacing minus n by like, and I've also changed this particular symbol as well, right? I'm just trying to index this particular thing in a manner that it should reflect that this is the coefficient of e to the power minus 2 pi iota nx. Are you getting my point? So just that dn, if I'm replacing by c minus n, does not mean that I'm replacing n by minus n. I'm just giving it as, I'm just taking it as a symbol, this c minus n as a symbol, which is actually representing the coefficient of e to the power iota 2 pi minus n x and t. It's nothing else. So that at least, after all, I'm going to write it. You may be saying that why do you take c minus n? Just to say that this would be something. I'm not saying that these are all equal. I'm just saying just to write that these are constants, nothing else. So don't worry about it. I mean, this is just a sort of a symbolic interchange, nothing else. So it has got nothing that I'm not writing n equal to minus n here. Had I written n equal to minus n, then I had simply written it as d minus n here. So don't worry about it. So understand my point. This is not that I'm replacing n by minus n. I'm just saying that replace dn by c minus n, so that it looks a compact version. So that now I can write and understand, after the end of the day, I'm not writing that all these cn's are same. I'm just writing that these cn's would be some constant. So that just like this e to the power minus 2 pi iota nx would become one single term. In short, I can say that my function, if it is a periodic function, I can represent it in terms of a complex Fourier exponential series. And this is it. This is one thing. Now the question arises, the first question that comes to the mind is, let's say this is fine that we have, and now let us see also what were the constant. So Cn was equal to what? It was equal to An minus iota Bn upon 2. And I think An, if you see, it was 2 upon, now 2 will come because of this. It was 2 upon 2. It was from minus t by 2 to beta plus t by 2. And it was fx into cos of 2 pi. I think it was iota. And then you had n x upon t. And then I had, I think, uh, uh, minus iota sine of 2 pi iota n x upon t. And why it is happening this way, iota is why it is accompanied, because see here, this is iota. So you know what is bn. Bn can be extracted from fx into sine 2 pi iota n x upon t, and you have to just place 2 upon t. I think this is quite clear. So I can do is this, I can write it in this fashion, 1 upon t from minus t by 2 to plus t by 2, and this is f of x. And what is this? This is simply e to the power of minus iota 2 pi n x upon t, and this is dx, where n is greater than 0. So this is your Cn, and similarly you can find your Dn also. So your Dn would be equals to what? Your Dn would be equals to, I think, 1 upon t. I'm writing it without derivation. E minus t by 2 to plus t by 2. This will be f of x, and then you will have e to the power of iota 2 pi n x upon t, and then there will be dx, where n is greater than equal to 1. Okay, so basically this is Dn, or you can write it as c minus of n. This is same, one and the same thing. Okay, so one thing is quite sure. One thing is quite sure, that what can be written is, this is quite sure that I can now write very evidently one thing, that a periodic function fx with period t having finite number of discontinuities. This you will learn when you will learn Fourier series. Right now just understand having finite number of discontinuities in one period. Note, in one period can be expanded can be expanded in a complex Fourier series. In a complex Fourier series, f given by f of x. Just understand, if what does it mean? It means that you can write your complex Fourier series, like you can write it from uh, minus infinity to plus infinity. This is 2 pi iota nx upon t, where Cn is nothing but it is equal to what? Cn is nothing but it is equal to minus d by 2 to plus d by 2, and it will take care of everything. F of x where n can belong to any integer now. Okay, so you see, instead of dn, when you were writing dn here, it was simply not minus n, rather it was n. And here if you see, when you were finding cn, it was minus n here. So basically I can compactify and write it in this form. So one thing you have to understand, this is something called as your complex Fourier series, or you can say that it is a complex Fourier series for a periodic function. So one thing is quite clear, that this is a complex Fourier series, and these are called as your complex Fourier coefficient. Now the question arises that this is fine, that till now whatever we know, it is just an extension of what we've done in our graduation. Okay, so this is something that we've done in our graduation, that probably in Bayesian oscillations, this kind of things must have been done in your graduation classes. You were required to find what would be Cn, what would be Dn, and then now the question arises that this is fine for periodic functions. Okay, this is fine for periodic function. What about aperiodic functions? Can we have certain sense of uh, uh, functional representations? Okay, functional representations for the aperiodic functions as well. So this brings us to the central question of our first lecture, which is defining Fourier transforms. Okay, so this draws us to the central theme of our today's lecture. Although we are just going to have an introduction today, but this is what I want to this is the major theme of our today's lecture. So very often we are going to deal with aperiodic functions, like the functions which are not periodic. Okay, and understand the fact that one of the things that I'm just going to teach you today is how to visualize an aperiodic function. How to visualize an aperiodic function. So let's say I'll do one thing. I'll make 3 lines here so that you'll be able to get what I want to say. So let us make okay. Uh, so the central theme is that very often you will find that you are not dealing with periodic functions, rather you are dealing with the aperiodic functions, right? So what to do about them? What to do about them? So this is what is the central theme at first. So what I'm doing, it's I'm not making it to the scale. Just understand the fact. I'm just picturizing some of the things. Okay. So what I'll do, I'll take a periodic function right now. Okay, I'll just take a periodic function right now. Okay, and that periodic function, I'm making it a square input. You can take square pulse, you can say. So from -1 to 1, I'm taking a square pulse, and what I'm doing, I'm saying that this is repetitive. This is repetitive, and it will go on. Okay, so the first thing that I'm trying to say, let's say my function f of x is defined as simply 1 if mod of x is less than 1. So basically mod of x less than 1 means minus 1 to 1, your function is simply 1. And beyond that, your function is simply 0 if mod of x is greater than 1 and less than t by 2. So let's say this is your t by 2 here, and this is, let's say, minus t by 2 here. So from here to your function is 0. And given that your function f is periodic with period t, so what will happen if you add t to it? So basically this is t by 2. This, if you add t to it, so it will uh, start repeating the pattern after a transformation that f of x plus t is equal to f of x. So what does it imply? That if you add t, so again the same pattern will start on, you can say, repeating. So for example, again if you add f of x plus t, so basically what does it represent? It represents that this is, you can take these as a, what should I say, you can are you getting my point? This is square input and with period t. Is that clear or not clear? And you just take t greater than 2, otherwise you will get a problem here. So t greater than 2. Are you getting my point or not getting my point? देखो इसका मतलब क्या हुआ, f of x is equal to 1 if mod of x is less than 1. mod of x less than 1 मतलब क्या हुआ बेटा, x lies between -1 and 1. तो जब भी x -1 से 1 के बीच में, तो फंक्शन क्या है, 1 है, अदरवाइज क्या है, 0. और साथ ही साथ क्या बोला गया है, फंक्शन रिपीट्स सेल्फ इन अ पीरियड t. सो बेसिकली तुम जैसे t ऐड करोगे, सो दिस इज, लेट्स से दिस इज t by 2, this is 1 plus t then. So basically what will happen after t, so your function will repeat in a period, in a fundamental period t. And you will say, why did you keep this t? I want to vary this t. I want to vary this t and let you know what is happening. I would vary this t and let you know what is happening. So let's say if I make the t large, as large as possible. So if I make t large, let's say I'll help you with one example. Let's say if I take t equal to 2, what does it mean? It means that your function f of x is equals to 1 if mod x is less than 1 and f of x, नहीं t को 1 तो नहीं ले सकते, let's say t equal to 4 ले लिया मैंने, है ना, एक बार t को 4 ले लो, 1 ले लोगे तो t 1 से लेकर हाफ तो गलत हो जाएगा, t greater than 2 ही लेना पड़ेगा. So let's say t को 4 ले लिया. t को 4 लेने का मतलब क्या हुआ, जब फंक्शन 1 होगा, जब mod x क्या हो, लेस देन 1, दैट इज x जब -1 से 1 के बीच में हो तो फंक्शन क्या होगा बेटा, 1. और जब mod x 1 से लेकर 2 के बीच में, तो 1 से लेकर 2 के बीच में फंक्शन क्या हो जाएगा, 0. और 2 से लेकर 3 के बीच में फिर वो वापस से 1 हो जाएगा, बिकॉज f of x plus 1 is simply what, f of x. Is that clear? अब देखो थोड़ा समझने की कोशिश करो, अगर मैं t को लार्ज करता जाऊं, 100, 10,000, 10 की पावर बढ़ाता जाऊं, तो फॉर एग्जांपल इफ आई इंक्रीज माय t, so what will happen, the distance between these two square inputs would start enlarging, would start widening, you can say. So if I make t large, this will happen. And if I make t sufficiently large, let us take t tends to infinity, so what will happen, there only will remain one this kind of square input. See why? So if I take t tends to infinity, what does it mean? That now function definition has been changed to simply 1 if mod of x is less than 1, and if mod of x is greater than 1 and less than infinity, your function is 0. So basically what does it represent? That your function is everywhere 0. जब mod of x greater than 1 हो, मतलब distance from origin is greater than 1, less than infinity, इस पूरे distance के लिए 0 हो जाएगा, और एक ही बस ये. So what does it imply? That your function which is periodic can be made aperiodic if you take t tends to infinity. Is that fine or not fine? Is that fine or not fine? Or let's say another example I'm saying, taking. So for example, if I want to take an example of e की power minus mod x. So how do you make e की power minus mod x? You make e की power minus mod x this way. And I'm restricting the function till this only. Let's say till this particular point. Let's say this is minus t by 2 and plus t by 2. And now let's say that my function is periodic with period t. So what will happen? It is 0. At exact t, it will again show the same pattern. So it has at t, Again, if I take, so if I say that my function f of x is, I'll let you know what I'm trying to say. If I say that my function f of x is simply e to the power minus mod x for all mod x less than t by 2, and function fx is periodic with period t. So what will happen? This is a kind of pattern that you're going to observe. This is something that I'm also telling you. Try to make this on your own. Then you will understand what I'm trying to say. So period का मतलब क्या होता है? As it is repetition दिखेगा. देखो zero पे कैसे दिख रहा है? यहाँ point पे दिख रहा है. ऐसे t पे भी कहाँ दिखेगा? बिल्कुल point पे. t by 2t पे कहाँ दिखेगा? बिल्कुल point पे. So basically same pattern is going to repeat it. So e की power minus mod x का ग्राफ बनाया from minus t by 2 to plus t by 2, and it is repeating itself in period t. So basically what is happening, if I am trying to take t tends to infinity, so what will happen? It will be this, just this function. What is happening? This would be the function. It would be simply this. It will be simply e to the power minus mod x if t tends to infinity. And clearly this is an aperiodic function. So one of the ways to formulate the same theory for the Fourier series, or you can say, in other words, I'll take that. So for example, we knew that if I have this periodic function which has some finite number of discontinuities in one period, I can represent it in terms of your complex Fourier series, and then because I can write my sines and cosine in terms of the complex exponential form. So I can write my function which is periodic as well as having finite number of discontinuities in terms of the linear combination of a complex exponentials. That is absolutely fine. Now instead, one asks what is going to be a treatment if a periodic function is replaced by an aperiodic function. Okay, so if a periodic function is aperiodic function has to be represented in some sort of these complex exponential terms. So what is one way ahead? One way ahead is that we know that if I take my period as large as possible, t tends to infinity, then my periodic function would eventually become an aperiodic function. My periodic function will become an aperiodic function. My periodic function will become an aperiodic function. Is that clear? So what you can do, you can express your, one can express an aperiodic function. One can express an aperiodic function in terms of, or you can say that in you can say as the limit of periodic function as t tends to infinity. That is, as the period tends to infinity. Is that fine? And we want to express, or we can, I would say that we want to find an expansion, that is a Fourier expansion for such aperiodic functions. Is that clear? Or is that completely not clear? Okay, good enough. Chalo, so what I would do is, so I'll consider a general function where I'll take a counter over t. Okay, so I'll take a counter over t means I'll somehow put t into perspective. That is, I will consider, let us consider a general periodic function. So I'll consider a general periodic function, and that is f of t is equals to f of x plus t is equal to f of x. And what I'll do, I'll take this entire term as kn. This term, 2 pi n upon t, I'll take as simply kn, so that my things will become easy now. Okay, so now your Fourier series, which I wrote initially, I can write this entire Fourier series ftx as simply this. देखो ऐसे लिख सकते हैं इसको, देखो summation n equals to minus infinity to n equals to plus infinity cn e की power iota, and this will be kn x. Simply this. And I know what is my Cn. This is quite clear that my Cn would be equals to what? Cn would be equals to, so I'll write that only. Ftx would be simply equals to summation. I'll write 1 upon t here. This will become summation n equals to minus infinity to plus infinity. Now I'm going to replace what is my Cn. Cn is simply minus t by 2 to plus t by 2, and I will write this e to the power iota knx outside. And what is Cn? Cn is simply some, you take another variable, let's say f of u. This is e to the power of minus iota kn u and du. Just don't forget that this is your Cn. And why I've taken different symbol, otherwise you'll get confused. If I take x here, then you will merge this thing inside, and then things will become out of control clearly, because then it will become one. So understand the fact that the Cn is this. The Cn I have already found in the earlier expression, if you see here. Okay, so this is what we've done till now. Okay, so today in any case I'm going to do one Fourier transform, so at least you just get a zeal of it, and then a zest of it, and then from tomorrow onwards we're going to just focus on Fourier transform. I'm just trying to formulate the theory today. Okay, now what you can do is you can again see what would be kn plus 1 minus kn. So this represents the shift in k, and that is simply 2 pi upon t. So if I want to write my t in terms of delta k, I can do so also. I can write my 1 upon t as simply delta k upon pi. In fact, delta k upon 2 pi, I guess, right? Delta k upon 2 pi. Right? So this is what I can do. So instead of 1 upon t, I can do so. So I'll write this f t x is simply 1 upon 2 pi, and then I have summation n equals to minus infinity to n equals to plus infinity, and then you have this delta k, and then you have e to the power iota k n x, and then you have this integration from minus t by 2 to plus t by 2. This is f of u, and this is e to the power minus iota k n u du. Okay, or otherwise you can do that also, like I can push this inside, because obviously this is not a function of u. So what I can do is I can simply write it as 1 upon 2 pi, and this is f t x is simply summation n equals to minus infinity to n equals to plus infinity. I'll be satisfied with this delta k written here, so I'll write minus t by 2 to plus t by 2. Here I will get f of u, and I will write e to the power minus iota kn, and I will write, I think I should write here, I should take n this inside and write x minus of u, and then you have this du. And one of the main thing is that you have to understand is this. See, after all this, while you will integrate this up, this is finally a function of what? This finally would be a function of kn. Understand the point that this would remain a function of kn. Why this would remain a function of kn? Because see, you when integrated, and when you place the limit t by 2 to plus t by 2, it will remain a function of kn. It will remain a function of kn. So parameter kn would control this integral. So basically, if you take change the kn, the integral would change. So I'll write this as a function of k of n. And so function of k of n is nothing but it is minus t by 2 to plus t by 2 f of u, and then you have e to the power iota minus, and then I'll write kn x minus of u, and then you have this du. And eventually I can write that my function, which is periodic right now, just don't forget that this is periodic with period t, is written as 1 upon 2 pi sums over n equals to minus infinite to n equals to plus infinite, and this is simply capital F k n delta k. I hope it is clear. Now understand one more thing. We were actually interested in aperiodic functions. So for that we need to do one thing. We need to take t tends to infinity. And if I take t tends to infinity, two things are going to happen. One thing is very much clear, that this integral limits minus t by 2 to plus t by 2, this will become minus infinity to plus infinity. That is the integral limits in Cn. I'll write in Cn would go from not on Cn nahi, matlab ye wala fkn would go from minus infinite to plus infinite. This is one thing that is quite sure. Second thing is quite clear, that 1 upon t, this will tend towards 0. And another thing is clear, that the difference delta k, which was represented by I think 2 pi upon t, this will also go towards 0. So instead of delta k, you can also replace this as dk or all those things that we are going to do. Is that clear till now? So now what I'll do is, if I now replace, if I take n tends to infinite, if I take n tends to infinite, instead of k n, I'll drop this n now here. I'll simply write f of k is simply what? It is simply equals to minus infinite to plus infinite. F of u I can write as a f of u only. I will write e to the power iota minus, and this is not minus, I think this was plus only, sorry, my mistake. This was iota k x minus u du. Simply this. Is that clear? We have simply dropped kn and simply written as k as n tends to infinity. Is that clear? थोड़ा थोड़ा समझ में आया कि बिल्कुल समझ नहीं आया? देखो कुछ नहीं करना है. As t tends to infinity, your limits would go from minus infinity to plus infinity, right? Your kn would kn is equals to what? It is equal to 2n pi upon t. Okay, it is equals to 2n pi upon t. So basically just I have dropped kn because now it is no longer a discrete kind of thing. Now it is a continuous kind of thing, because as n tends to infinite, so your delta k would become very small. So basically it is not a discrete sort of case where you can use summation. So instead of summation, I will have to use, instead of kn, like kn, समझ रहे थे kn होता क्या था? Kn was simply 2 pi, delta k क्या था? 2 pi upon t, और kn ultimately क्या था? kn was 2n pi upon t. So it was sort of discretized. So instead of discretization, now I'm moving from a continuous version to the same. So instead of kn, which was actually taken care by 2 pi n, so now instead of kn, I'll drop the subscript n, because now I'm taking continuous case. I'm taking all possible values. Is that clear or not clear? And again, eventually understand this will remain a function of k, because see, if you integrate with respect to u, you place minus infinity and plus infinity, your u will disappear, only k would remain. So after all, this is a function of k. This will do also. You'll come to see all these things. Is that clear or not clear at all? बिल्कुल समझ नहीं आ रहा क्या? At least know me. Let me know. आ रहा है नहीं आ रहा? Good enough. चलो. So now you understand that your function f of x. Now as t tends to infinity, your ft, which was a periodic function, now you can say that this will become some aperiodic function, and let us say that this is f of x. And what is f of x? F of x was summation. Remember, ftx क्या था? Summation 1 upon 2 pi n equals to minus infinite to n equals to plus infinite. It was fkn, and then you had dk, delta k, sorry, delta k. Now instead of delta k, as n tends to infinity, your delta k would become very small, so I'll write it as dk. Your this limits, that is a sum, would again change into an integration. See, if you take n very large, what will happen? The difference between the difference delta k would become very small. So basically, you're adding almost on a, you're basically variably summing things. You're variable summing the things. So I'll write it as 1 upon 2 pi. The summation would be replaced by an integration. This will go from minus infinite to plus infinite. Fkn would simply become your fk, which is nothing but it is fu e to the power iota k x minus u, and this is du. And then again minus infinite to plus infinite. So why minus infinite to plus infinite? This is minus infinite to plus infinite of this. This is fk. This integration will also, this particular summation will also be replaced from minus infinite to plus infinite. So this summation would also be, it will also go from minus infinite to plus infinite. Okay, is that clear or not clear? Okay, so fx after all can be written as 1 upon 2 pi minus infinite to plus infinite minus infinite to plus infinite fu e to the power iota k x minus u du dk. And what I'll do, I'll simply write it in this fashion. Fx can be written as minus infinite to plus infinite. This I will write 1 upon 2 pi, and this is e to the power iota kx. This I'm separating it out, dk, and then I'm writing minus infinite to plus infinite fu e to the power iota minus ku du. This particular term I'm replacing by either f tilde k or gk. And what I'll do, instead of writing 1 upon 2 pi, I will distribute 1 upon root 2 pi. So I'll distribute 1 upon root 2 pi. So what I'll do, I'll write that my f of x, okay, so your f of x is simply, or you can say your, you can say g of k, sorry, your g of k is simply 1 upon 2 pi integration from minus infinite to plus infinite, and you have this f of u e to the power minus iota ku du. Okay, is that clear? So I'll write f of u e to the power minus iota ku du. Whether you write q or whether you write x, it is one of the same thing. So 1 upon 2 pi from minus infinite to plus infinite, it is f of x e to the power minus iota kx dx. Is that clear? Or what I can do, I can also write that my f of x is simply what? F of x is simply, if I've taken 1 upon 2 pi here, so what I'll do, or you do one thing, you just write it as 1 upon root 2 pi here and 1 upon root 2 pi here, just for symmetric constraints. So what I'll do, 1 upon root 2 pi here, and what will f of x will become? F of x will be simply 1 upon root 2 pi integration from minus infinite to plus infinite e to the power iota kx gk dk. So this is what is your gk. ये पूरा जो एक्सप्रेशन बेटा वो क्या gk तो है, ये gk है. So you can write that your f of x is nothing but it is equals to e to the power iota kx gk dk, or your gk is nothing but it is equals to 1 upon root 2 pi integration from minus infinite to plus infinite f of x e to the power minus iota kx dx. This 1 upon root 2 pi I have done for symmetric reasons. Don't worry about it. So many a times in your examination you'll find that teachers don't give this kind of constants. So it depends upon question. So it is not necessary that you put. Even if you don't put, then also it is fine. But right now I have done it in sort of symmetric sense. Is that clear or not? So this is what is referred to as your Fourier transforms. So these are referred to as Fourier transforms. So your Fourier transforms are defined as simply f of x is defined as 1 upon root 2 pi from minus infinite to plus infinite. This is gk e to the power iota kx dk, and what is gk? Gk is 1 upon root 2 pi minus infinite to plus infinite. This is simply f of x e to the power minus iota kx, and then you have this dx. I hope it is clear. So basically, both of them are called as Fourier transforms of each other. So at times you will be thinking कि किसको Fourier transform बोले. So at times this is referred to as a Fourier transform, but this is also Fourier transform. So both of them are called as Fourier transform of each other. Okay. So for example, I'll say that if gk is my Fourier transform, if I say that my gk is Fourier transform, this is my Fourier transform right now. So this will be inverse Fourier transform. This will be my inverse Fourier transform. Okay, so understand that these two integrals are only varying in the signs, right? So these two integrals are only varying in the signs. These two integrals are only differing in the signs of the exponent, nothing else. So what is happening, what I can do is that, so most often you say that this is the Fourier transform of this particular function, this is the Fourier transform of this particular function. So basically both of them are called as Fourier transform of each other. Okay, and this brings us to the main problem of our today, that is called as your Fourier integral theorem. And what does it say? It says that if a function f of x, if a function f of x possesses no more than a finite number of discontinuities, no more than a finite number of discontinuities, and if this particular integral is convergent, absolutely, because if this is not convergent, then this will be a problem, is absolutely convergent, or you can say is finite, this integral must be finite, then f of x can be simply written as minus infinite to plus infinite g of k e to power iota kx dx, where gk is called as your Fourier transform of f of x. I hope it is clear. I hope it is clear. So physically, what does it represent? Physically, what does it represent? I would say that, uh, for example, when you had this kind of square wave input, let's say I had this, what is happening? Let's say we had this square wave input. Just give me a minute. Okay, when we had this square wave input. So by simulations, if you see, if you do a simulation on internet, on your MATLAB or somewhere, what you can do is you can simulate this particular thing. So for example, if you this is your square wave input, and if you're going to write it in terms of periodic function, what will happen? Uh, what will happen that the sign, if you write it in the linear combination of sines and cosine, they will start wiggling about here. More and more sines and cosines you take, more and more number of terms you will take, it will start wiggling over the square wave input only. This is how it is going to behave. So what is the story? The story is very simple, that in Fourier series, so I'll write it here, the Fourier series is only for what? Of a periodic function. What does it tell? It tells us what frequencies, or you can say wave vectors, that is k, because frequencies after all related to k also, of sinusoidal functions we should choose, or we should choose, या फिर we should superimpose to replicate the original function, replicate the original periodic function. So this is what your Fourier series does. So Fourier series helps us in what? Fourier series of a periodic function will tell what are the frequencies, and what all those frequencies I should select for the sinusoidal function, so that if I superimpose, I'll get this. Okay, and in turn, what is Fourier transform? Fourier transform is for your aperiodic function, because you have taken t tends to infinity. So Fourier transform of a function would tell, Fourier transform of a function would tell what frequencies, or probably amplitudes as well, what frequencies and amplitude, because cn's you have to find, no? So amplitudes we combine, or we superimpose. Now superimpose in what limit? Not in discrete limit, rather in continuous limit, from minus infinity to plus infinity, in order to get, or in order to you can say replicate, or in order to, you can say, uh, resemble, like sort of resemble the original function. And now here the restriction is not it should be a periodic function, original function, simply original function. Rather, I would say aperiodic function also this would give you. So I'm not saying you cannot find a Fourier transform to an periodic only for aperiodic function, but in general you can do so here. For Fourier series, you had a constraint that you can do this Fourier series only for periodic function. One should understand for a Fourier series, one needs only discrete frequencies. You need just the discrete set of frequencies. And here there is a continuous set of, you can say, here you have a complete range of, you can say rather, you have this continuous range of frequencies. And what these frequencies would generate, these frequencies when put under this sinusoidal function would generate an appropriate resemblance to aperiodic function, to an aperiodic function. So in general, as far as mathematics is concerned, these kx and anything would not mean anything, like k or x, anything would not mean anything. So for example, if someone asks what is the dimension of k, okay, if someone asks what is the dimension of k, so you know that because it is on the exponent of this. So if, for example, if it has a dimension L, then k will have dimension L minus 1. So this is how it is. In physics, you can talk of the dimensions of k. In physics, you can talk of dimensions of k. So basically, it happens in which sort of space you are working in. So for example, if you are working in time domain, so basically if you are working in time domain, so this t would imply your time, so your k would imply inverse of time, or basically it would imply your sort of frequency. Is that clear or not? Okay. So tomorrow we'll start with Fourier transform of some very basic functions, and as we go along, you'll see that this is a very, very rich topic as far as physics is concerned. So please pay heed to this topic. So I'll meet you tomorrow. Till then, take care.